Welcome back. Uh, Welcome back, everyone. Good to see you all. So our plan for this week would be we'll continue talking about dynamic programming for this lecture. And in the next lecture, we'll actually talk about, start talking about linear programming. So we've seen three examples of dynamic programming, 3 or 4 examples. And all of them used different kinds of subproblems. So we'll see a couple more examples of dynamic programming, and maybe you'll see some on the homework. And the goal is to just sort of see all the different kinds of subproblems there is, or not all, but at least many of the different kinds of subproblems that you encounter. Sort of a lot of the problem solving is really pattern matching between what you have seen earlier. Although we hate to admit it, there is some creativity, but also a lot of it is just comes out of some part of your memory. And so it's sort of nice to actually just see the different kinds of subproblems that you encounter. And, it sort of adds to your arsenal when you try to attack a new problem in DP. So today we'll see 2 examples. So the first one is minimum triangulation. So here's the problem. So the problem, the input is just n points V1 through Vn that form a convex polygon. And let's say these points are given to you in, let's say, counterclockwise. This would be clockwise along the polygon. So just given n points that form a convex polygon. So it's just your input is a polygon, and your goal is to divide the polygon into triangles such that you minimize the total length of all the edges. So you want to find the minimum cost triangulation. Okay. So where minimum cost being you want to minimize the total perimeter of all the triangles. Okay, so for example, your input could look like this polygon here. It's a hexagon. And you could triangulate it in many ways. So a simple triangulation would be that would be one way to divide it into triangles. Another way would be and you could think of many other okay. You can divide a polygon into triangles in so many different ways. And what you want to find out is what's the way to divide it into triangles so that you minimize the total perimeter of all the triangles. So in this case, the total perimeter of this triangulation is the perimeter of this triangle, which is, I'll just use the letter L for lengths. So it's L. So for this one, the total perimeter is there's L 1, 6 plus L 5, 6 plus L 1, 5. So that is this triangle. And then you add it up over all the different triangles. It's L 1, 5 plus L 4, 5 plus L 1, 4. That is this triangle plus L14 plus L43 plus L13. That is this triangle, and L12 plus L13 plus L23. So that's the total cost of this triangulation. It's the total perimeter of all the triangles. I mean, this is the specifics of the cost function is not super important. You could also have minimized the total length of all the diagonals or things like that. This particular cost function is, I think, especially clean in terms of the recurrence relation and so on. But you know, don't worry about too much about the very specifics of the cost function. Okay, so that's what you want to minimize. You want to know. I mean, if you want a more physical thing, you just have a polygon and you want to cut it into triangles, and you want to minimize the total length of all the cuts that you're going to make. Okay, that's essentially the same thing, because the total perimeter of all the triangles is twice is basically proportional to, or basically varies the same way as the total length of all the diagonals that you've drawn, which is the number of cuts you're going to make, the length of all the cuts you're making. Any other questions? Okay, so that's the problem. So let's see how to come up with a sub-problem for this. So we want to devise an algorithm using dynamic programming for this problem. So as usual, the first step is to come up with a sub-problem. Okay, and the technique which I sort of use in my mind is to imagine the optimal solution, right? So, you know, let's say this is suppose I have a polygon, and suppose this is my optimal solution. Okay, and so now I'm imagining this optimal solution, and I want to break it up into smaller parts, each of which is somehow optimal. So one thing you could try is to just do the following. The first thing that comes to mind is, okay, let's look at, if you think of this as a piece of paper you're cutting, you could just try to say, let's make the first cut. So you have this polygon and this polygon. Okay, 1, 2, 6, 2, 3, 4, 5, 6. Okay. So you made the first cut. It's going to be some diagonal, and then you have 2 pieces, and now you need to cut the pieces into triangles in the smallest number of cuts. You could try this. I think you can make this strategy work, but one needs to be careful with doing just this, because let's take this a few steps down the way, right? Let's see what happens if we made a few cuts, right? Or if we keep breaking up this problem into sub-problems this way, let's see what happens after a few steps down the tree, down the recursion tree. Well, you know, let's say in general, I might make some other cut here, and to arrive at this solution, I need to make some other cut here. And so in general, at some point, I will end up with some subset of points. Okay? And some subset of points could be some arbitrary subset of points, and then the polygon connecting them. Okay? And I need to cut them into pieces, right? So the question is, you know, dynamic programming is really recursion with memoization. I should have said this earlier. It's just really recursion with memoization. So as you break your problem into pieces, into smaller subproblems, you don't want a really long list of subproblems that you want to solve. Okay? For example, if you take a convex polygon and if you pick any subset of points there, any subset of the points, there'll be some convex polygon formed by just those subset of points. Right? For example, if I just pick 1, 3, 5, 7, 9 alternate points, they'll form some convex polygon. Every subset of points that you pick will form some convex polygon. Right? So a list of all subproblems would be, for every subset of points, for every polygon that you can get from those points, find the best way to cut it. Right? But that's a really long list of subproblems because there's one convex polygon for every subset of points. Right? So all I'm saying is, you started out with the list, or, in this case, you start out with cutting this polygon, trying to cut V1 through Vn, and somehow as you're cutting it, if you start getting all kinds of pieces, right? If you start getting all kinds of pieces, at some point, you'll have some subset of points. Okay? And the convex polygon formed by them. And you need to figure out the best way to cut that. So that's true to the n subproblem, because for every subset, if you have a convex polygon and you try to cut it, you're in trouble. So all I'm saying is that when we're trying to break up this problem into optimal solution into subproblems, we want to make sure that we don't get too many different looking pieces. Right? We want to get a few subproblems, a smaller number of subproblems. If I just cut it start breaking it up arbitrarily, I'll end up with subproblems which look arbitrarily crazy, all sorts of convex polygons which use subsets of these points. Instead, we want to do it in some order so that we don't get arbitrarily bad pieces. So here's the sort of the trick. So the trick is, let's actually, I think, so here's a observation, sort of a silly observation. If I look at any edge, vi plus 1, any edge of this type, any edge, it must participate in some triangle. Right? Of course, every edge of the polygon participates in some triangle. Okay? So you could try to split it based on that. You could ask, okay, let's just look at the edge. Let's look at the edge 1, 2. Okay, consider the edge 1, 2. Okay? Now 1, 2 has to be part of some triangle. Which triangle is the edge 1, 2 part of? Well, it could be part of 1, 2, 6, or 1, 2, 5, or 1, 2, 4, or 1, 2, 3. Right? We don't know. But in the optimal solution, 1, 2 is part of some triangle. And it could be one of these cases. Okay? So let's say just to continue this thought experiment, let's just say 1, 2 is part of this triangle. Let's just say, suppose it is this case. Then you see that what I'm left with is the problem of triangulating two polygons on either side of this triangle. So I'll have to triangulate this piece, and I'll have to triangulate this piece. Okay? But because I'm sort of trying to do this in an orderly fashion, I'm doing it this way, you can see that the pieces I get are not arbitrary subsets, but are contiguous sections on the polygon. Meaning, this part of the, let me use a different color here. Yeah, this polygon is really the section formed by, if I look at vertices V2, V3, V4, that is this green section. Okay. What about this one? Well, if I look at pieces, if I look at the vertices V4, V5, V6, V1, Okay, it's a contiguous section of the vertices on the polygon. If you're walking clockwise, it's some section of the vertices in the polygon. If I look at V4, V5, V6, V1, the polygon formed by those is this one. Okay? So basically you see that the pieces are not completely arbitrary, but they are contiguous sections of the original polygon. And there are much fewer contiguous sections of the original polygon. I just need to pick a start point, Vi, and an end point, Vj, and every vertex between Vi and Vj, that's one section of the polygon. And how many choices are there? Well, the start point can be one of n choices. This end point can be one of n choices. There are n squared different sections of the polygon, contiguous sections of the polygon. So that's a smaller number of subproblems than having arbitrary subsets. Okay, so this seems like a reasonable thing. So it seems like what we want to do is to figure out optimal way of cutting a polygon that's formed by Vi to Vj for some I and j. Okay, I'll write down the definition of subproblem now. Okay, here's a subproblem. Let me say Tij, where I'm assuming I is less than j. Sorry, no, I shouldn't assume that. Just Tij is the cost of triangulating the convex polygon formed by Vi, Vi plus 1, Vi plus 2, up to Vj. Okay, sorry, I should say minimum cost, the optimal cost, or the minimum cost of triangulating the convex polygon formed by this. Those are my subproblems. So if I look at T of 1, n, that's my answer. That's the answer that we're looking for, right? Okay, that's just the entire polygon. Okay? Okay, so now we have the subproblem, and we can just write a recurrence right away. Okay, so let me just erase this label so that it's not confusing. So here is I, okay, and then you walk into I plus 1 up to j. Let's say j is here, okay, I plus 2 and j, okay, and you're only interested in the polygon from I to j, this section of the polygon. You're only interested in this section of the polygon. Okay? And you want to figure out the optimal way of cutting this section of the polygon into triangles. Okay? And then our natural approach is, let's look at the edge I, I plus 1. If you look at the edge I plus 1, it has to be part of some triangle. So I'm trying to write a recurrence relation now. So if I look at the edge I plus 1, it has to be part of some triangle, meaning it must have some other vertex with which it forms a triangle. So let's say I plus 1 forms a triangle with a vertex k here. Okay, so this vertex k could be I plus 2. For instance, I plus 1, I plus 2 could be a triangle, or I plus 1, I plus 3 could be a triangle, and all the way till I plus 1, J could be a triangle. Okay, one of these possibilities. Okay, let's see what's happening in each of these cases. Suppose I look at a case where it's I plus 1, and K. For some K is a triangle. Okay, then you have, on the one hand, the polygon from I plus 1 to K. Sorry, my pictures are not very good today. You have the polygon from I plus 1 to K, right? That need to separate. So that's going to take cost exactly I plus 1 comma K. And then you have the polygon from K to I, which you need to triangulate. So that's going to cost you K to I, T of K comma I. And then finally, you have the finally you have the triangle I plus 1K, which is, I'm just going to write it as perimeter of I plus 1K. Okay. And we don't know which of these vertices from I plus 2 to J is part of the triangle, but we know that the optimal one will pick the minimum of them. So it's the minimum of these possibilities. So that's the recurrence relation. Question, please. The question was, why do I add T, K to I? I think probably the part of the confusion is my picture is not nice enough. I think I lost the picture that I had earlier. So let me draw the picture again. So. I hope this picture helps. So you have the polygon that's formed by vertices from I to J. Okay? And what I'm doing is I'm asking which triangle is I plus 1 part of. It's part of some triangle I plus 1K. And then if I use the triangle on the left and the right, I get two different polygons. And the cost of those polygons are given by T I plus 1 comma K and T K to I. And then the perimeter of the triangle that we just separated out. Yes? Okay, great question. The question is, how do you know that the Tk to I would be a continuous set of edges? Well, it is not contiguous, but for one jump, right? So let's see how this thing looks like. So let's just say I is 2. Let's say I is 2, and J is 10, and N is 50, okay? So basically you have 2, 3, 4, 5, 6, 7, 8, 9, of course, yeah, I don't know how to count, 9. And then, so if you follow the indices in increasing order, the sequence will go increase from 2 to 9, and then it jump back to 2, right? So, at all times, if we look at the convex polygon Ti to J, or the polygon formed by Vi to Vj, it consists of one contiguous section with one jump. And if you take that and you cut it, you see that both the sides still have contiguous sections. You can see that I plus 1 to k is a contiguous section. And k to j is also, k to I is another contiguous section, where by contiguous I mean you can have one jump. Right? You're going to have one loop around when you go from 1 through n and back to 1. Right? When you go from 1 through n back to 1, there's going to be one place where you go from a larger value to a smaller value. Just that one jump. But apart from that, you will be contiguous. Yes. Okay. This has exactly n squared subproblems as I've defined it. Right? It has exactly n squared subproblems because we're looking at subsections of the polygon where you define two endpoints and then you look at the section between the two endpoints. Yes?
How do you know what to make that jump from a large number to a small number?
Oh, it's the definition of the subproblem. So t of, let's say n is 50. If you ask me t of 25, 3, you count up from 25, 26, 27, 50, 1, 2, 3. If you ask me what's t of 3 to 25, it would be all numbers from 3 to 25. Question? Yes.
How do you know that the jump is going to be from like n to 1 if you're just taking an arbitrary polygon from j to I?
So the question is, I think the point of confusion is, how do we know that we always have a contiguous subsection, right? And we don't end up with more complicated subsections as we make the cuts. Okay? And I think one way to see it is to see it through induction. Okay? So let's define the contiguous subsection to be, you have, if you give me I and j, if I is smaller than j, I should just go from I to j. If I is bigger than j, then I should go from I up to n and go to j. That's the definition of a contiguous subsection. It's really, geometrically, it's just, you give me two endpoints, starting point, I walk clockwise along the polygon from the start point to the end point. That's my definition of a contiguous subsection. Now, if you take any such continuous path, clockwise path along the polygon, and you break it anywhere, you will get two paths which are both contiguous at all times. Right? You're not going to get any other kind of path. Right? So that's why all the sub-problems that you end up, as you break up your path, will be paths which will be sub-paths, counterclockwise paths along the polygon. Okay? That's, okay. Yes, let's.
How do you know the distance between two consecutive points? Is it encoded in the input?
Okay, the question is, how do we know the distance between two consecutive points? Let's assume for the moment it's encoded in the input. Or we could, if you're given the coordinates of the endpoints, we can calculate the distances. Yes.
Yeah, so I was going to ask, I was a little bit confused. Like, for example, like in the blue shaded area, don't we have like two jumps that aren't like contiguous? Like I'm pretty sure like I to J and I to J both of them. So I'm just getting a bit confused as to why those things are happening.
Right, I and j are not necessarily next to each other. And so the question is really, why don't we have two jumps here as we cut this?
I guess like as a follow-up, right, we're like when we do like k, comma I, we're doing like all the points from k to I, but we're not really doing all the points from k to I, we're doing all the points from k to j and then I. Yeah.
Right. Yeah, I think I made a mistake here. Uh, I can, so the, okay, so the issue is that um, we should always make sure we have contiguous sections on the path. So what we should do is we should look at the start point and the end point of the path and see which triangle they are part of. So if I look at here, if I to j is a contiguous section on the path, and I ask which triangle is ij part of, then I'll break it up into two pieces, which are again contiguous sections on the path. So, I'm sorry about this. So I think the key mistake I did was I shouldn't look at an I and I plus 1. Let's see which triangle is I and j part of. Which triangle is I and j part of? Okay. So I and j is an edge of the polygon now, and is the edge of a polygon that you're trying to cut, and that's the jump edge. That's where you're that's the edge from the end point to the start point. And which triangle is that part of? It has to be part of some triangle. So let's say it's part of some, I to k or k to j. So if it's part of, if there's an edge, if there's a triangle ijk, then you will break it up into t I to k, k to j, t I to k, t, let me write here. So it's going to be t I to k, t k to j, sorry, I think it's a mistake here, t k to j, and then you would have the I, j, k triangle. Right? So, okay. All right, yeah. Yes. Oh, I'm sorry. What's the question?
Why is the bottomless subproblem from I plus 1 to
Oh, sorry. Yeah, actually, let me just. Okay, I think. Okay, I think a lot of questions will be answered if I do it once without any mistake, and then it'll be very clear. Okay, so let's start. I'm sorry about this. I'll try. Okay, let me draw a polygon. Okay, so this is my polygon, and then I have my vertex I here, and then my vertex j here. Okay, and I have this jump edge. Okay, this is my polygon. This is my piece of a polygon that I have. Okay, now I need to cut it into pieces. As I cut it into pieces, this jump edge k has to be part of some triangle. Okay, I don't know which triangle it is part of, but let me just say it's part of this triangle k. Okay, and then what do I end up with? Well, t of I comma j is, well, this vertex k can be, right, the triangle that could be there is I plus 1, I plus 2, I plus 1, I plus 3, or all the way to I, j, I, j minus 1, j. Okay? Right. So it could be one of these two cases. K can be, here K is I'm sorry. Okay. So here K is either equal to I plus 1, I plus 2, or up to j minus 1. Right? K can be one of these vertices in between I and j. Okay? And depending on which case it is, let's say it is, you're in the case where I, j, k. Okay, let's say you're in the general case like that, then the total cost is T, I, k, because you need to triangulate this part. And then T, k, j, because you need to triangulate this part, plus the perimeter of the triangle I, j, k. Okay? So it's the minimum of these n possibilities. Okay? Does it make sense? All right. Yeah. I'm sorry about this. It was, yeah. Okay. Good. Okay. So we've seen a few dynamic programming algorithms so far. Let me just, summarize a few different kinds of subproblems that we've seen so far. Okay. So, so the kind of subproblems we've seen is, firstly, you can have, if you have strings, right, one possibility is a prefix. You can think about prefixes, or then you can think of suffix. If you have a pair of strings, x and y, then you can sort of think, it's usually when you have pair of inputs or a triple of inputs, then it's usually good to think about product constructions. So meaning, if you had a single string, you can look at all prefixes of that string. If you had two strings, you can look at every prefix of this and every prefix of this. If you had three strings, prefix of each of them, right? So if you had two strings, you can think about prefixes of x. So your subproblems could be, for instance, prefix of x, comma prefix of y, right? These sort of product constructions are it's always useful. Or sometimes prefix of x and suffix of y, and so on. I think the reason we looked at this triangulation problem is because it has this nice different kind of subproblem. In triangulation, we had all possible sections. So if I have a input of length 1 through n, there are n prefixes, right? There are n suffixes. But then if I look at sections, like contiguous sections in the middle, I have n squared sections. So these are contiguous sections that go from I up to j for all I and j. Right? That's what happened in this polygon example. We sort of looked at for every start point and end point, we looked at the section between the two. So that's a different one. Another one which you would see, probably not in class, but maybe on the homework, is if you have trees in your problem. If you have a tree in your problem, it's often useful to look at subtrees, rooted subtrees. So just by rooting a tree at a node, making some node the root, now every other node falls, you get an ordering. Every node has a descendants and ancestors. And now you can look at subtree subtrees of that tree. And these are very useful. If you have problems on trees, they're often very easy because you can do dynamic programming on subtrees. In fact, most problems, a lot of problems, optimization problems on trees are easy because of this reason. Okay, and finally, sometimes you have no recourse but to look at all possible subsets, things like with exponentially many subproblems, but this is an example for TSP. We'll probably, or Hamiltonian path, we'll probably see that later in the class. So, and I think on the homework you'll see a few other kinds of subproblems which sort of don't fall into any of these categories. But these are things to keep in mind, just patterns, and you can sort of reuse them. Okay, any questions I can answer? Yes. Okay, so I think, all right, so let's, the question is, was the question about what was the mistake in my previous attempt? Yeah. Okay, good. Let's see where I went wrong. Do people see where I went wrong? How many of you see where I went wrong? Okay, so here's a English way to say where I went wrong, okay? So when you try to go, let's try to say in English what a subproblem is. Okay? In English, just a subproblem in my world is, okay, I'm given this polygon. I can walk on this clockwise, 1 through n, and come back. Okay? That's my thing. And my subproblem will be, if you start at I, if you give me I and j, I'll walk from I to j in the forward direction, and then in the clockwise direction, and whatever polygon that I cover, that's my subproblem. Now, what's the property that I want from the class of subproblems is that when I break it up, I should see more of the same. I should see more of the same. I shouldn't see new kinds of problems that I need to solve. I should see more of the same. So I have a walk from I to j. Like, think of a walk from like vertex 2 to vertex 50. In a really long cycle. There's a really long cycle, and then just a vertex 2 to vertex 50, like a little 48-step walk. Okay? Now, if I break it up, I need to break it up into pieces such that each of them looks exactly like my subproblem, meaning each of them should look like a walk in the clockwise direction for some number of steps. So if I look at a walk, and then I have vertex 2 here, vertex 50 here, it's part of a bigger thing. But now, if I take some triangle like this, and I break it, okay? So now what are the kind of subproblems that I'm left with? Well, you see that this one is nice. This one is really looks like a walk. Okay? What about the other one? Does it look like a walk? No, it looks like there's this part, and there's like a big jump. I need to include 2. Right? So it doesn't look like my subproblems. So as I break my problem into subproblems, I need to make sure that everything looks like something that I already solved. Here it does not, because one part is nice. It looks like a contiguous section. The other part looks like there is this section on top, and then there is isolated vertex 2 that I need to include. Okay? And we don't want that. Okay? And what we instead did was the following. We said, okay, let's not look at what triangle is formed by 2 and 3. Let's look at what triangle is formed by 2 and 50. Okay? Now, if I look at a triangle formed by 2 and 50, wherever it is, the 2 sections are contiguous sections. So I get problems which look just like the problems I started solving. So that's the mistake I did. So, okay. So it's really about how I broke up the subproblem where I made a mistake. As I said earlier, if you break it up in arbitrary ways, you'll get arbitrary kinds of pieces, and then it gets more complicated. We have to break it up in a way so that when we write the recurrence, in a way so that each of the pieces looks exactly what we want to. Yes.
So like now we're moving that vertex along instead of the top vertex. Is that what that means?
So now, I didn't get the question.
Well, that middle vertex in between 2 and 15. Now we're moving that one along.
Yes. The vertex K that's in between I and J, we look at all possible choices for that. Okay, yes, go ahead. Yes, actually I didn't mention the runtime for this problem, the runtime for this algorithm, but I didn't even mention the order in which we'll do the recurrence, the subproblems, solve the subproblems. I'll let you figure it out. The runtime is NQ. Any other questions? Okay, we'll stop here, and next class we'll start linear programming.